Hi. So hi everybody, I'm Axelle Apvrille. I'm working at Fortinet. I'm their mobile malware analyst. So just in case you don't know what that means, it means I just get an awful lot of mobile malware every day to analyze and to disassemble and hopefully to understand what they're doing and detect afterwards, of course. I'm not going to lecture you really about mobile malware on Android and all that stuff. It will be a very short introduction of, what's the importance of mobile malware today. I think that probably all of you have heard that really it's growing very fast on Android. I've got this nice chart there showing a peak for Android with regards to other platforms. To be honest, it's been nearly over 1 year, 1.5 years, that people have been claiming that Android is really full of malware. Actually, it's shorter than that. We saw the peak arriving only like 6 months or at most 1 year ago. And before that, we still had an awful lot of mobile malware on Symbian, the Symbian platform. Because what people tend to forget is that there's maybe perhaps even now much more Symbian phones in the world than Android platforms. So this is the kind of mobile malware that we get. Those are only recent ones, those that I got in, since the middle of September. We get a lot of toll fraud, SMS toll fraud. Those are mobile malware that are sending SMS to premium phone numbers. And, well, they get some kind of substantial revenue from that. And the other kind of malware that we see pretty much is also spyware. And those are going to, I don't know, for one reason or another, spy your SMS messages, spy your locations, spy your call logs, who call themselves browsing logs, things like that. If at one time you want to check what are the recent mobile malware that we're catching, well, you can go to the URL down there and you'll have, the recent entries, very recent entries. Also, the other thing that we're seeing is that, well, since there has been kind of a growth on Android malware there, well, now we can see even some hits, some the kind of the infection rate, which is the download hits that we have for those malware on Android, and we see that, well, we're getting a lot of hits for a few samples, such as Droid Dream, for instance, on Android, and something like, well, the charts show something like in between 100 hits per month. The fact is that this is only the hits that we get through our FortiGates. So, well, people who don't have FortiGates don't get any hits, of course, and only when the stats are enabled on the boxes. So it's pretty much underestimated there, of course. It still means that, every month there are people, a lot of people, hundreds, which are trying either to download a malware and probably install it afterwards, or getting infected one way or another. So that's all about what I'm really going to talk is more about, more advanced stuff on Android reverse engineering. I don't know if some of you were at, well, yes, I think so. Some of you were at Insomnihack, which is another security conference in Geneva in March. And I talked about the kind of usual tools that we're using when we want to reverse Android. That is APK tool, Smalley, Backsmalley, those kind of tool. You can download my slides there. Today I'm going to deal with some kind of new stuff, things a little bit more advanced that I think some of those you haven't seen yet outside in the world. So a little bit on the compilers, and also we'll be playing pretty much with the text format. Already discouraged. Then I'll be doing a short demo and also explaining a few stuff on how to evade emulator detection when you're a malware or when you're challenged, that kind of stuff. So the decompilers. We've got, I'd say, 4 main decompilers that we can use. 2 of them are not specific to Dalvik. They're specific to Java, that is Java decompiler and DJ. And we've got some others, DED and DAD, very similar names, which are kind of specific for Dalvik, but all those 4 can be usable on Android malware to decompile and get some handsome code to look at. So what I wanted to do here is I took a malware, recent malware, and with FakeMark, which was really which was out like 1 month or a little bit more in France, and it was specifically targeting France. So that's why we had a specific look on it because I'm based in France. And I asked all those 4 decompilers to decompile a pretty standard, not really so tricky function, get key code there, and we'll have a look at the differences. So this is what Java decompiler will output. I think it's quite okay the way it looks like. The only thing which is a bit surprising is the while true loop that you have at the beginning, at the top there. Don't really know why that is it's there. It's a bit strange. And of course there are a few issues that I can't mention there, but I mean that I can't show on the slide, is that Java decompiler is prone to crashing. So there are a lot of functions that it will say, I'm sorry, I can't decompile it, I haven't managed to. So sometimes you have to fall back to another decompiler. DJ decompiler, so it's the same function, exactly. Same one. Looks like it's a bit different. I find this perhaps a little bit more ugly because you've got a lot of go-tos, which is not very nice for Java programming. And also you've got a strange instruction at the beginning, monitor enter. That is because this is a Java decompiler and doesn't know the specifics of Dalvik. So didn't spot that one. With DED, DED, I can't show you what it gave out because it crashed on that function. So there's got just, I decompiled another function there, another one, the second part. And it's okay, except that you've got a lot of casts, as you can see, object, R6, Kevin, and the variables are not named, so you've got R6 for the 6th register and things like that. So maybe not so good. And then that is included actually most of the time in AndroGuard, if some of you know that tool. And it gives also a pretty good output, except that it's a bit kind of lengthy because everything has the full path of the name of everything before it. So you'll have com to boy world of goo full before the actual name of the function. So that's a bit lengthy. And you've got also always in nearly every function that it decompiles the synchronized keyword, which I don't know why it's there all the time. So the goal here is not to say that one decompiler is actually better than the other one. It's more just to show you that there are really some specifics, some specific output that you'll have with one decompiler and not with another one. So that if you find something a bit strange when you decompile with one, you can know if it's just that it's always outputting that kind of stuff, or if you have to fall back and try another one to see what really the code would look like, of course. So that's all for decompilers. Now, the DEX format. So DEX is Dalvik executables, right? And like all formats, file formats, well, it begins with a header, okay? You've got the header where you've got most of the things, and then you've got plenty of arrays. Arrays which are full of indexes that will actually point to the last part of the file format, which is the data section. So let's say you write some code end with, I don't know, a hello world. Well, the hello world, the string itself will be in the data section, so down there in the yellow box. And you'll have the string array that will reference that string and provide an index for everybody who's using that string there. If you have the name of a method, I don't know, get my ID or something like that, well, that also for Dalvik is a string. So you'll have it in the yellow box there, down there in the data section. And you'll have the string array reference that string. And you'll have, as it's a method, you'll have the method array reference the string index in the string array. Okay, so it's all a lot of indexes there to not repeat strings and only have strings occur once in the format. Those are the main references that you'll have to look into if you want to start playing with the text format. When you'll have my slides, so you can just click there and go to the references. So we have the text format, and we want, most of the time what we want to do is have a look at the header first thing. So if you want to have a look at the header, there's one tool written by Tim Stratzeri, and it's not a very well-known tool, but you'll find him on his blog, and it's called DexInfo. It's very simple. You just call Java DexInfo and provide the text file. It will read and output the header of the text. If you don't want to do it that way, you've also got Androlyze, which is part of AndroGuard, with an interactive script shell there, and you can tell it first thing, load my classes.dex, so that's the first line of it, then get the header out of that file, and then print it header.show, and you can see what you've got in there. Like all header files, it starts with a magic, and the magic for the text files is dex, and most of the time I've seen 035. Actually, the specification says it can be a little bit another number too, but what we see is 035 most of the time. If you want to parse a bit more than just the header, well, you can use 010 editor, which is really very handy there, because it will you load your text file with also a text template, and then it will show side by side the format and then what's inside that particular part of the format. So it's really very easy to parse text files with that. Then, if you want, there's a third way to play with text files is with AndroGuard, because AndroGuard has implemented just a set of tools, a set of classes to read each part of the text file. So you've got a class to understand the header, that's called header item. You've got a class for the string array, string item, for the types, type ID item, for everything most of the time. And if you want to get one of those objects of those classes, well, you just call one of the methods that you've got, get header item, get field ID item. It's always the same kind of name that you've got there. And once you've got one of those objects, well, you've got most of the time always the same names of functions that you can use to play, parse with, or show what's in that object. So you can show it. That means it will show the disassembly of it, so the Smalley code for it. You can also print the hexadecimal bytes for that part. So that's get row for get the row buffer. You can also get its position in the file, so that will be the offset, gets the index, and you've got also, of course, some other shortcuts if you just want to do something which is very typical, such as read all strings that are in the dex file, well then you just call a function called getStrings and it returns it all. At first, it seems perhaps a bit difficult to remember all the names of the functions. The very cool thing with it is that when you're using Androlize, it's an interactive shell, and you've got some completion for commands. So you just start and type in the beginning of the command, and you'll have the rest of it appear, which is very good. Those are just a few examples there. If you want to list all the classes, for instance, in a dex file, so it's get classes names, and you've got them all. If you want to get all methods, well, this time you just do a very short Python command where you get all the methods for a given method and then show all that you have for that method. So yeah, that's all for that part. So now we're going to see kind of a use case. A few months ago, Dex Labs released a challenge, which was really interesting there, and it concerns obfuscating bytecode. What they were doing there is that actually they were hiding the real payload of, the real code of the challenge inside something that would look like the payload of an array. Okay, so in that right part, the dark brown part. So if you were just disassembling the code instruction by instruction, you would see first a goto, and you'd say, okay, it's just a goto. Then you'd see the fill array data instruction, and you'd say, oh, I'm gonna have an array, and then you'd read the other instructions within there, which are the payload. You would read them as the payload, as the contents of the array, and not as real instructions, Dalvik instructions. On the contrary, so let me get to the next one. Yeah, on the contrary, if you disassemble and be a little bit more intelligent at the way you're disassembling, and you see that the first goto is always going to occur. So here what happens is that it tells you if a variable v0 equals v0, okay, that is always going to happen. We're going to skip 9 words later, plus 9, and it's in words. So we're going to skip 18 bytes later, and that just happens to fall at the beginning of the payload of the supposedly data array. And then you will read the subsequent data as real Dalvik instructions and not just as a payload of an array there. So the way, the official way the challenge was solved there was using AndroGuard, was to say, okay, we're gonna have the disassembler point to the beginning of the payload, and we're gonna tell it, to have a look at this specific index. So the method is called setCodeIndex, and we tell it to go 18 bytes later, and it will start and disassemble at that port. And that way we could see, well, the real Dalvik code. So it's starting to build strings, and then it will get the application context. So that's a nice solution, and it worked, but actually setCodeIndex was written specifically to solve the challenge, and I think it wasn't really, it wasn't necessary. It is possible to solve the challenge without this specific function. And I'm going to show you how. And it is also possible with my solution to actually disassemble in a DEX file at any offset. You choose the offset and it will disassemble that part. Of course, if you choose an offset that is not meaningful, well, of course, you're just going to disassemble crap. But if you want, you can just put it at the exact points that you wish to disassemble. So this is the other way to do it. Basically, in that case, what we wanted to do is, that's right, is to disassemble at the offset, which is the beginning of the brown box at the bottom there. But when we are in a method, the beginning of a method is contained within a structure which is called a code item. And at the beginning, you've got plenty of fixed variables there that hold the register size, the size for the inputs, for the outputs, plenty of other stuff. And all of that take 16 bytes. Okay, so we're gonna have to pass by, we can get the location of the beginning of code item, that is the code offset. Then we've got to skip 16 bytes, and then we have to skip again 9 words, that is 18 bytes again. So 16 plus 18. And then what I have done is actually write a tool for AndroGuard, which is just a Python helper script that will disassemble at any offset that I give for the DEX file. AndroGuard is open source, so I will send out my script to them so that they include it in the repository. So, time to wake up, as I said, and it's demo time. There we go, with a nice big font so that everybody can read, hopefully. Is it okay? So, what we're going to do is I'm going to show you exactly that part live, and I'm going to launch AndroGuard. There it goes. And Crack Me Obfuscator is the DEX Labs challenge. Okay, so I don't remember exactly the name. There we go. I can use completion. Analyze APK. Crack Me Obfuscator. And I just specify also which decompiler I want it to use if I wish to use a decompiler. Analyze APK outputs three different outputs which will go in the variables A, D, and DX. Then I can do plenty of things with that, and it's quite interesting. For instance, I can show you which is the main activity of the challenge. Okay, it's the drop activity. I can show also, I don't know, the permissions. What is it doing? Oh, okay, it's using the internet permission. So that's just part of the cool thing that we can do. Now we're going to have a look at more specifically, well, the activity that we're concerned with. So we said it was drop activity. And we can inspect all the methods that we have there. So the one I'm really interested in is called exec. And we're going to try and show it. So now it's not an error there, it's really, yeah, there we go. So we have there exactly what we are decompiling, and we see that we have a fill array data, then the fill array payload, and it doesn't look very much like that. And we've got the go-to exception, the go-to instruction, sorry, which is down there at the bottom. If we try to use the decompiler, it's not going to work because, of course, it doesn't understand very much out of that data payload, so we get an error. Now, if we do it the official way, we set the code IDX, and we say it's 12, and we do that again. And yeah, okay, so then it works, and we see the decompiled code, and it's really much more readable there. And if you want to have a look at it in Smalley, there it is, and it is also completely different. There you've got the strings that we're building at the beginning, here again, then getting the application context, all that stuff. So now I'll do it my way. So I have to reset it so that I'm not cheating. Set it back to IDX0. And as this is a bit lengthy, I'm going to rename it exec method and say that like that. Exec method. Now I need to get the offset of the beginning of my method, so I think it's get off. Get. No. Let's get code off. Sorry, so that's the offset for that. 219,900. Okay, so, and I need to get also the length of the code block that we have to see how much we're gonna decompile. So get code, get in size, so that's the size of the instructions that we have, and we have 108 bytes there. Now I'm going to decompile it. First I need to get the dex file. I had analyzed an APK, so what's the dex? So the dex is I get dex. And then in my dex, I have the row buffer for the dex file inside that APK. Okay? And I use decode, DCM. The length is 108 minus 9, because we said we're skipping 9 words. Then my dex, and I tell it where to read. So it's 209,900. Plus I said we're skipping 16 bytes. The 16 bytes for the registers, the input size and everything. And then 18 bytes because that's where we're pointing to for the beginning of the array. And this is just a random stuff where to stop reading. And oops, we're gonna show the result of this. And there it goes. You can see again, decompile it. Fine, we've got the string, building the string, getting the application context, all that stuff. So that's the way to do it with AndroGuard without my script. And if you want to do it a little bit more quickly with the script, so set AndroGuard, and I called it AndroDis for disassembly. You got a very quick helper for the usage. So input is the dex file. So the dex file is in that directory. Yep, it's in there. And the offset, so it's 219,900 plus 16 plus 18, so that's plus 34. And there we go. Okay, string builder again, you recognize the real output there. Okay, so that's all for the demo. Back to the slides. Yeah, that was in case the demo did not work. You see, I've got the backup slides. So now we saw how to play with the dex file and all that kind of stuff. If we have played and modified a dex file, it's not going to work straight away afterwards, because there is in the header a checksum and a hash for the dex. Okay, so if you want it to be acceptable afterwards for the Android platform, well, you have to rechecksum and to rehash. So I've written this very small tool that is on GitHub there if you want to have a look at it, but it's really nothing extraordinary. It's just rehashing, checksumming the text file, but it's handy in those cases there. When you've rehashed it, then if you want to repackage the APK, it's also very simple. You really need to get all the ingredients, so you get the modified classes.dex, and you also get everything, all the other things that you need, which is the assets, the resources, the Android manifest. You zip all of that, and then you do a jar sign on that. It's quite simple to do it with a makefile, actually. On a totally different aspect, sometimes also when we're analyzing malware or doing things like that, it's useful to know our device ID. So if you want to know your device ID, the easiest way to do it is write a simple application and ask for what Android calls Android_ID and just display it. That's one of the easiest ways. If you're not into application writing and you don't want to do that, the other way to do it is you get a shell on your device, and then you go into a database that is called settings and look for the secure table in there, and there's also a field called Android_ID, and you can either read the value for that there, and if you're root, you can also modify it. Now, some other interesting stuff, I think, is evading emulator detection. Because we have, of course, sometimes malware that don't want us to be looked into from an emulator, and they'll behave totally differently on the emulator than on a real device. But on the other hand, from an analyst's point of view, it's very cool to be using an emulator because the devices just don't always happen to work the way you expect them to. So, how do they detect the emulator? Most of the time, they do it by checking for system properties, and they look for the expected values that all Android emulators will return. For instance, they will say that the product name is SDK, that the product brand is generic, and all that stuff. So they'll check for that. And if it has the specific value for the emulator, well, then I'd say, oh, sorry, this is an emulator, I'm going to do this or that instead of my normal behavior. They can do that on a coding implementation point of view, either by calling the getProp command, that's from the shell, or from a method called get in the system properties class. So this is a crackme that was out from, again, Tim Stratzeric there, and as you can see, it is detecting that it's running on an emulator. And as I wanted to solve the challenge and I wanted to do it completely, I said, I'm gonna work out that it doesn't detect it's on the emulator. So we saw that it's just checking for the properties there. So what are we going to do? Well, we have to understand how the properties are being returned. So from an architecture point of view, if you get the properties, you've got two entry points. Either you're getting it from getProp, which is the shell command. So this is on the right side of the slide, and then it will go into that is implemented actually in the toolbox part of it. And in the end, it goes down to libcutils. If you're using system properties .get from the Dalvik framework, the virtual machines, then it is going to Android system properties, then to GNI part of that, and then relying at the bottom again on libcutils. So of course, what we're going to do is we're going to hook the getProperties function at libcutils level. Okay, and whenever somebody is asking for, I don't know, a row product brand, we're not going to return generic, but either something real that you fancy or whatever name, anything that's actually the challenge or the malware is not going to recognize as something part of the emulator. It's not actually gonna work if you hook all system properties at libcutils. There is one property, row kernel QEMU, that you cannot hook at libcutils levels, because if you do, the emulator is not going to boot at all. So this one you've got to hook it a little bit, just a layer above at the GNI level. And once you've done that, well, what you have to do is, of course, you recompile your emulator, and then it works. It's not detecting it's running on the emulator. Last part also we're very much concerned with when we're analyzing mobile malware is, of course, SMS. We want to know what the phone is going to send as SMS, what it's going to receive, all that kind of stuff. So on the SMS language, well, the cell phone is always communicating with what we call an SMS sender, SMSC. If we're using an Android emulator, well, what happens is that we can very easily read what the emulator is sending as SMS by just having a look at the radio logs. Okay, so this is the command adb logcat /b radio, and we can read what's going out there. We see the SMS in PDU format. If we want to send an SMS to the Android emulator, then we use telnet, and it will send it to the emulator. So that's helpful. That works. That's just what it looks like. If you want to have a look at the PDU, that's the PDU of an SMS. We can also use some other libraries. We've got a Python messaging library that will help you encode from the Android emulator's perspective PDUs. So it will encode SMS submits and decode the deliver part. So that's what it looks like if you want to send an SMS from the Python language with that part. But actually, it's not very helpful in our case, well, for a mobile malware analyst, because what we really want to do is not to encode an SMS submit, but we want to decode it, and the other way around, for the SMS deliver, we want to encode it. And those parts are not included in Python messaging. So if we want to decode the PDUs, for instance, what we can do is use another tool, which is called PDUspy. This is a Windows tool, but if you're just a Linux addict or a Unix addict, it also works with Wine. So, and it will decode the PDU and show you the phone number, well, all the details that are included in the SMS, the phone number, and of course the body of the SMS. Or you can use, of course, an online decoder that works too. There are a couple of there out on the web. Okay, that's about all. I just wish to mention, of course, that I've designed an Android challenge. It's still out and running, of course. And, well, if you're the first one to find the solution and bring it to Fortinet's booth, which is over there, well, you'll be hopefully lucky to win a FortiGate. The challenge is downloadable from the Hashdays website if you want there. And hopefully things that I've said there will perhaps help you solve it or not, or I hope anyway you'll have had a good time looking at the challenge and listening to the talk. And this is all my details if you want to contact me later for this stuff or others. I think we perhaps have time a little bit for questions if some people have questions.